As we discussed in previous videos, neural networks are inspired by the human brain. And as the name suggests, the neurons in neural networks are based on the biological neurons in the brain.
Depending on the input signals, a biological neuron could fire or not. Similarly, in artificial neural networks, activation functions decide whether a neuron fires or, in other words, activates, and if it does, how the output should be transformed. This adds nonlinearity to the network, which helps learn complex patterns. We will look into a couple of widely used activation functions in this video.
So, what if we don't use an activation function? Then it's simply equivalent to a linear equation. This is also known as the identity function, since the function doesn't do anything to the output. It spits out the value it was given.
Mathematically, it can be represented as shown here. We can use this commonly in regression tasks where the output needs to be a continuous value. Even though this is computationally efficient and doesn't suffer from the vanishing gradient problem like the sigmoid does, this can result in underfitting and poor model performances. In such cases, nonlinear activation functions such as ReLU can be used to improve the performance of the model. ReLU stands for rectified linear unit. It sets all negative values to 0 and passes all positive values unchanged. The main point here is that the ReLU function does not activate all the neurons at the same time. Since only a certain number of neurons are activated, the ReLU function is far more computationally efficient when compared to the activations like sigmoid.
Mathematically, it can be represented like this. This is used in many neural network architectures, including CNN and RNA. However, ReLU can lead to the dying ReLU problem. This occurs when a large number of neurons output 0, resulting in a dead network that hinders its learning any further. To overcome this issue, leaky ReLU can be used. Leaky ReLU is an improved version of ReLU function to solve the dying ReLU problem, as it has a small positive slope in the negative area. Leaky ReLU is commonly used in deep learning models, especially in CNNs.
Mathematically, it can be represented as shown here. This is computationally efficient, similar to ReLU, and has a relatively simple implementation. But the choice of the slope of the negative part of the activation function is subjective and can affect the performance of the network. If you want the output to be mapped to 0-1 range, sigmoid is the go-to function, which is also known as the logistic function. For example, a probability should be in 0-1 range. Therefore, sigmoid function is widely used in binary classification problems.
It can be mathematically expressed as shown here, and its graph looks like this. As you can see, as the input moves away from 0, the output approaches either 0 or 1. Derivative of the sigmoid is shown here, and its graph looks like this. As you can see, as the input moves away from 0, the gradient approaches 0. This is known as the vanishing gradient problem. Therefore, engineers might go for ReLU in some cases, since it's also computationally more efficient than sigmoid. Hyperbolic tangent function, which is also known as tanh, is quite similar to the sigmoid, but here the output is mapped to -1 range. This can be a useful choice in neural networks, where the output needs to be centered around 0.
It can be mathematically expressed as shown here, and its graph looks like this. As you can see, as the input moves away from the 0, the output approaches either -1 or 1. Derivative of the hyperbolic tangent is shown here, and its graph looks like this. As you can see, just like the sigmoid, this also suffers from the vanishing gradient problem. Okay, this one is a bit different from the ones we discussed previously. Softmax is commonly used in the output layer of multi-class classifiers, where the final output vector should represent probabilities between 0 and 1, and the sum of those probabilities should equal to 1.
If the output vector has n values, softmax can be mathematically expressed like this. As you can see, these values will fall between 0 and 1. And if we take the summation over the n values, we can see that it equals 1.
If you enjoyed this excerpt, please like and share. If you have any suggestion, feedback or questions, don't hesitate to comment.
And to stay tuned, please subscribe and hit the bell icon. See you soon.